Hello everyone, welcome back. This is lecture 22 of the lecture series Signals and Systems. In this video, we will be learning about the methods of finding the inverse Z transform and then see about the properties of Z transform, and also we'll see some common Z transform pairs, and finally we'll take a look at unilateral Z transform. So let's get started. Methods of finding inverse Z transform. So in the previous lecture, we already saw one of the method, which is nothing but partial fraction. So in that, what we did, we represent x of z in the form, let's say x of z equal to summation I equal to 1 to n some ai divided by 1 minus ai z inverse. So then what you can do, we can take the inverse Z transform depending on the ROC or the region of convergence. So case A, if the ROC is outside the pole z equal to ai, then it means your ROC is mod z greater than ai. Then what will be your inverse Z transform? So it will be of the form of a power n u of n or a power n u of n. And since this constant term is also there, you will have a power n u of n, giving you Z transform of ai by 1 minus ai z inverse and mod z greater than ai. So similarly, if the ROC is inside the pole z equal to ai, this again we discussed. So you will have minus ai power n u of n minus 1. Minus n minus 1. Correct? So this is having a Z transform of same ai by 1 minus ai z inverse, but its ROC will be mod z less than ai. So depending on the ROC and the pole location, you have to take the respective inverse Z transforms. So we'll see a short example. So we'll use the same example we used in the last lecture, except for the change in your ROC. Okay, so I have x of z equal to 3 minus 5 by 6 z inverse by 1 minus 1 by 4 z inverse into 1 minus 1 by 3 z inverse. And your ROC is mod z less than 1 by 3 greater than 1 by 4. So in partial fractions, we already derived in the last lecture. Fraction form, we can write x of z as sum of these two entities. So 1 by 1 minus 1 by 4 z inverse plus 2 by 1 minus 1 by 3 z inverse. So let me call this as Z transform of x1 of n or x1 of z, and this one as x2 of z. And your ROC is mod z less than 1 by 3 less than 1 by 4. So if I write x1 of n, which is having a Z transform of 1 by 1 minus 1 by 4 z inverse, and what will be the part of ROC corresponding to this? It will be mod z greater than 1 by 4, correct? Similarly, if you are x2 of n, you have a single pole at 1 minus 1 by 3 z inverse, which is at 1 by 3. So here your ROC will be less than 1 by 3. So now you can find x1 of n and x2 of n. So x1 of n, since it is greater, so which one you have to use? You have to use case A. So ai, and this is 1 by 4 power n u of n. ai is 1 here. So you will have 1 by 4 power n u of n. Similarly, for x2 of n, you have to use case B, which says minus ai a power n u of minus n minus 1. So I'll have minus 2, right? This is 2 here. So minus 2, and what is your ai here? It's 1 by 3 power n u of minus n minus 1. So what will be your x of n together? It will be sum of these two signals. So I will have 1 by 4 power n u of n minus 2 into 1 by 3 power n u of minus n minus 1. So this is how you solve by partial fraction form. So the second method will be using power series expansion. Power series expansion. So in this case, what you're going to do is, you're going to represent x of z as follows. So you will have x of z equal to some, let's say, a n z power n plus, or we can use a minus n z power n, a minus n plus 1 z power n minus 1, and so on, plus a0 z power 0. So it will be just a0 plus a1 z inverse and so on, plus am z power minus m and so on. Here also this is. So you are representing x of z as power series expansion of z, right? Then comparing it with your x of z definition, so you have x of n z power minus n. So your x of n will be nothing but an in this case. So for each n. Okay. So this is straightforward because the coefficient of each power of z, right, gives you the direct value of x of n at that particular n. Okay. So we'll see some example. Example 1. So let's see a straight away example. If x of z is given as some 4z square plus 2 plus 3z inverse, and your ROC is given as 0 less than mod z less than infinity, because it is finite, right? And you're not including 0 and infinity, because at infinity, if you see, if you substitute here, this x of z will go to infinity, and for 0, 1 by 0 will give you infinity. So 0 and infinity are not included in this ROC, but all other z values are included. So from this, what you can say, your a2 is equal to 4, or this is a minus 2, right? So you have n and minus n here, so you have to be careful with that. And your a0 is equal to 2, and your a1 is equal to 3. So what will be your x of n? So your x of n is nothing but 4 for n equal to minus 2, 2 for n equal to 0, 3 for n equal to 1, and 0 for otherwise, right? All other cases. So this you can also write it as 4 delta of n plus 2 plus 2 delta of n plus 3 delta of n minus 1. And you very well know that your delta of n minus n naught is going to give you a z transform z power minus n naught, right? Your delta of n will give you a z transform 1. So 4 delta of n plus 2 will give you z power 2, delta of n give you z power 0, and 3 delta of n minus 1 will give you z power minus 1, 3 into z power minus 1. So this way also you can do it. So let's see some other example also. So not every time you will get this easy form, right? Sometimes you'll also get some difficult form. So let us check it for this one. This one we already know the answer, but still we'll try to solve it using this method. So your ROC can be mod z greater than a or mod z less than a. So we'll see first for mod z greater than a. So mod z greater than a denotes that x of n is right-sided sequence, right? This we know from the properties of our ROC, correct? So how will it look like? It will have some summation n equal to n1 to infinity x of n z power minus n. So this will be your z, x of z, and you will have some x of n1 z power minus n1 and so on up to infinity, right? So you will have some negative series in n also, correct? As it goes on, you will have some negative series in the powers of n. So we will be using our long division method to find the coefficients. So our numerator is nothing but 1 here, and your denominator is 1 minus az inverse, right? So I can write my denominator in two ways. I can write it as 1 minus az inverse, or I can put minus az inverse here plus 1. I can write it this way. So there is slight difference between the two. So in each case, we'll be concentrating on this first term, and we'll put some multiplier here or quotient here such that we can exactly cancel this 1 here, correct? So that is what we do. So let us see how we are doing for each case. Okay. So 1 minus az inverse, and we have 1 here. So to cancel that, our quotient will be 1. So we can write 1 minus az inverse, and we take a minus sign. So this will cancel. You will have az inverse here. So again, to cancel az inverse, I need to multiply this by az inverse. So I'll have az inverse minus a square z inverse square, right? Again a minus sign, this will cancel. I'll get a square z inverse square. Again, to cancel this, I need to multiply it with a square z inverse square. I'll get a square z inverse square minus a cube z inverse cube. So this will keep going on, right? And so on. So what is my quotient here? So my x of z, I can write it as 1 plus a z inverse plus a square z inverse square. Again, I'll get a cube z inverse cube and so on, correct? And this I can compress and write it as summation of n equal to 0 to infinity a power n z power minus n, correct? So what will be my x of n? My x of n is nothing but a power n, and since the summation itself is starting from 0, I need to add u of n here, okay? So this, if you see, I'm getting u of n. So we'll also try this case, what happens here, okay? So now I need to cancel this 1 by multiplying something with minus a z inverse. So to cancel this a, I need to multiply it with a inverse, and to cancel this z and bring it to 1, I need to multiply it with z. And then to cancel this minus sign, I put another minus sign here. So now I'll have 1 here also. So minus, and then I have to multiply this. So I'll get minus of a inverse z. So when it is coming down, it will be just a inverse z, correct? 1 will go away. And to cancel this a inverse z, what should I do? I should multiply this with something so that I get a inverse z. So which is nothing but minus, I need a inverse square and z square. Okay, so then I'll get a inverse z minus this into this will give me a inverse square z square. Again, if I take minus, this term will go away. This term will remain minus a square z square, and I need to keep multiplying this and until I reach infinity, correct? So if you see the difference here, what do you have here? You have positive powers of n, correct? So then how you can write your x of z as? I'll use a different color. Okay. So my x of z here is minus a inverse z minus a inverse square z square minus and so on. So I can write it as summation n equal to minus infinity to 1, correct? Or minus 1, a power n, and I have minus sign, z power minus n. If you see, this will hold true, right? For minus 1, you will have a power minus 1, z power 1, which is this term, and you also have a minus sign. Similarly, it will continue for up to minus infinity. So this is nothing but your x of n being a power n minus a power n u of minus n minus 1. It is starting from minus 1, right? I mean, it starts from minus infinity and ends at minus 1. So you use u of minus n minus 1. So this will be your other case of the ROC, right? For mod z less than mod a. This is for mod z greater than mod a, correct? And in our case, this is what we require in this. They have given mod z greater than mod a. So we should take this one as the answer. And if mod z was less than mod a, if that was given as an ROC, your x of n will be this value. So even if you start with the wrong method, you should quickly realize when you are getting positive powers of positive powers of z and negative powers of z. So negative powers of z means it is right-sided signal sequence. And positive power means it is left-sided. And depending on your ROC, you should also know which will be left-sided and which will be right-sided. And you should take the results accordingly. So even if you start with this and you're getting positive powers, you should quickly shuffle them and try to do it again, right? That way you can arrive at the answer. So we'll also see some other example where the x of z is not a rational function. So if you have x of z equal to log of 1 plus a z inverse and your ROC is mod z greater than mod a. So this also means that your a z inverse mod is gonna be less than 1. So if you have this log function, log of 1 plus x, and if you have x less than 1, so we'll have x minus x square by 2 plus x cube by 3 minus x power 4 by 4 plus and so on for your mod x less than 1. Because otherwise there is no way of proving whether this will converge. Only if this is less than 1, it will converge. Okay. So then this you can write it as summation n equal to 1 to infinity minus n whole power n plus 1 x power n divided by n. Okay. So similarly your x of z, you can write it as summation n equal to 1 to infinity minus 1 power n plus 1. In place of x you have to write a z power minus 1 power n by n. So this is nothing but summation n equal to 1 to infinity minus 1 power n plus 1 a power n by n z power minus n. So this, if you observe, is nothing but your x of n. So your x of n is minus 1 power n plus 1 a power n by n. And if you notice the summation, it is starting from 1. So which means that you should also include u of n minus 1. So these are the two simple methods of finding your inverse Z transform without actually implementing the inverse Z transform equation. Okay. So now let us move on to the properties of Z transform. So let me write out the Z transform and its inverse just so that it is easy for us to refer. So the Z transform equation is x of z equal to summation n equal to minus infinity to infinity x of n z power minus n, and our inverse Z transform is x of n equal to 1 over 2 pi j closed integral x of z z power n minus 1 dz. So you should be careful with this n minus 1. Okay. So our first property will be the linearity property. So if my x1 of n has a Z transform x of z, x1 of z and ROC equal to R1, and x2 of n has Z transform x2 of z with my ROC, then my Z transform equal to 1 over 2 pi j. So if my x1 of n has a Z transform x of z, x1 of z and ROC equal to R1, and x2 of n has Z transform x2 of z with my ROC, then my Z transform equal to 1 over 2 pi j. So if my x1 of n has a Z transform x of z, x1 of z and ROC equal to R1, and x2 of n has Z transform x2 of z with my ROC, equal to R2, then my AX1 of n plus BX2 of n, what will be its Z transform and ROC. So you can take x of z as summation n equal to minus infinity to infinity AX1 of n plus BX2 of n into z power minus n, and this you can break down into a summation n equal to minus infinity to infinity x1 of n z power minus n plus b summation n equal to minus infinity to infinity x2 of n z power minus n. So this is nothing but a x1 of z plus b x2 of z. So this will be your z transform. And your ROC will be intersection of these both. Or in other ways, if there is some pole cancellation, then the ROC might also extend beyond them. So it should contain at least R1 intersection R2. Okay. So which means that if there is, by chance there is a pole zero cancellation, then this might extend. Okay. So you can again think of simple examples. This we already discussed in the Laplace transform. So I'm moving on. So my next property will be time shifting property. So this is also straightforward and similar to what we discussed in the Fourier transform. So if you have your x of n having a z transform x of z with ROC equal to R, then your x of n minus n naught will have a z transform. So if you see from this equation, where x of n minus n naught will come as z power n minus n naught. So z power minus n naught, you can take it outside. So then the remaining will be your x of z, x of n. Or in other words, if you have to find x of z for that, this x of z into z power minus n naught, z power n minus 1 dz. This is what you will get, correct? So I'll write it down. So x of n minus n naught is equal to 1 over 2 pi j closed integral x of z, z power n minus n naught minus 1 dz. So this is nothing but 1 over 2 pi j integral x of z, z power minus n naught into z power n minus 1 dz. So this will be your z transform of x of n minus n naught. So x of z into z power minus n naught. And your ROC will again be R, but it can also add or delete. So union, addition or deletion of origin or infinity. So this you can reason out why, right? So if you just have delta of n, then your ROC is, this is 1 and your ROC is entire z plane. So if you push delta of n minus n naught and n naught is positive, then you will have z power minus n naught. Now you can't include 0 in the ROC. So ROC equal to z plane minus 0, correct? For n naught greater than 0, and ROC equal to z plane minus infinity for n naught less than 0, because you will have positive power of z and you can't substitute infinity. So that is why this plus addition or deletion of origin or infinity. So that one you have to take care. So your next property will be scaling in the z domain. So if you have my x of n giving a z transform of x of z with ROC equal to R, then I scale x by x of z by z naught. So if I scale this, my ROC also will change depending on the z naught. So if z naught greater than 1, then it will mean my ROC is expanding. My entire z plane itself will expand, right? And if my mod z naught is less than 1, my ROC will contract, or it will shrink, correct? Then how will I write my ROC? It will be Z0 into R. So if Z0 is greater than 1, it is gonna expand to mod Z0 R, and if Z0 is less than 1, it is gonna shrink or contract. So what will be my discrete time domain signal then? So if you observe, your x of z is equal to summation n equal to minus infinity to infinity x of 1 z power minus n, correct? Now if I substitute z by z0 here, I will have summation n equal to minus infinity to infinity x of n z power minus n by z0 power minus n. Z0 power minus n, 1 by z0 power minus n is z0 power n. So this is nothing but summation n equal to minus infinity to infinity x of n z0 power n z power minus n. So this will be my signal. So z0 power n x of n. So this will give a Z transform that is either like expanded in the frequency domain or in the Z plane, or contracted in the Z plane. So this is our third property, scaling in the Z domain. So as a special case of this, if your Z0 is equal to e power j omega naught, then what will happen? E power j omega naught n x of n will gonna give you a Z transform of x of e power minus j omega naught z. So what it means, only your phase of z is going to change, which means that it is rotation in the z plane. So which also means that shifting in frequency. Okay. So multiplication by a complex exponential of the form e power j omega naught n will cause a shift in frequency domain. Okay. Or shift in frequency. It will cause a rotation in the z plane or a shift in frequency, because rotation in z plane is nothing but e power j omega minus omega naught, something like this, right? So it is like a shift in the frequency component omega. So this will be our third property. So fourth property, let us see time reversal. So if you have x of n giving a z transform x of z with your ROC equal to R, then x of minus n, what will be the z transform? So we need to find it out. So what equation shall we refer to? So I need to get x of minus n here. So let me take the first equation. X of z equal to summation n equal to minus infinity to infinity x of n z power minus n. So I replace n with minus n. So your summation is again going to go from minus infinity to infinity. You will have x of minus n z power n. So now to bring z power minus n here, what I'll do is I replace z with z inverse. Okay. So z to z inverse. So then I'll get summation n equal to minus infinity to infinity x of minus n z power minus n. So then this will, the z transform of x of minus n will be x of z inverse. And my ROC will be nothing but, so suppose let's say your R was nothing but your mod z greater than A. So now your new z is nothing but, it is replaced with z inverse. So 1 by z is greater than A. This is your new ROC, right? Or R new L, right? So your ROC will be 1 by R, represented by 1 by R. So this is the definition for it. It is just your mod z will be great, your 1 by mod z will be greater than A. If your original ROC was mod z greater than a. So then you can rearrange this to get mod z less than 1 by a. So this will be your new ROC. So you can also observe that your right-sided signal has become a left-sided signal. So that is what you are also supposed to observe here. Okay. So our next property will be time expansion. So this again we saw it in our discrete time Fourier transform. So we describe our time expansion as xk of n given by x of n by k when n is a multiple of k, and 0 when n is not a multiple of k. Okay. So in that case, what will make xk of n give us the Fourier, the Z transform. So my x of n, let's say it gives a Z transform of x of z with ROC equal to R. So if we just try to write its Z transform, so it will be summation n equal to minus infinity to infinity xk of n z power minus n. But using this property, what can we say? It will be summation n equal to minus infinity to infinity x of n by k z power minus n, and also n is multiple of k. So I can replace n with some mk and I can sum it over m, correct? Summation m equal to minus infinity to infinity x of m z power minus n is replaced with mk. So this is nothing but summation m equal to minus infinity to infinity x of m z power k power minus m. So this is nothing but, it looks like z of x of z power k, correct? So your x of z is nothing but summation n equal to minus infinity to infinity x of n z power minus n. So this is not, looks like z is replaced with z power k. So that is what I have written there. So your new z transform for this signal, which is having a time expansion form, is nothing but x of z power k. So what will be your ROC be? So if your original ROC R was z greater than a, then your new ROC will be z power k greater than a, or mod z greater than a power 1 by k. So if, let's say, b is included in the ROC R, then b power 1 by k will be included in the ROC R new. So I can write your new ROC as, again this is z x of z power k, and your ROC will be R power 1 by k. So here also it was same. If b is included in your ROC here, so your mod z b will be some greater than a, then your 1 by b also will be included in your new ROC, because 1 by b will be always less than 1 by a, given that b is greater than a. So that way also we can interpret this 1 by r as. So here also it's straightforward that r power 1 by k. So next property we look at conjugation. So if my x of n has a z transform x of z, my x conjugate of n, what is it gonna have? So let me start with this summation n equal to minus infinity to infinity x of n z power minus n. I'll take conjugate on both sides. So I'll have x conjugate of n and z conjugate of minus n. So again I'll replace z with z conjugate. And notice that z conjugate of conjugate is equal to z itself. So my x conjugate of z conjugate is equal to summation n equal to minus infinity to infinity x conjugate of n z power minus n. So this is my signal and this will be my Z transform. So X conjugate of Z conjugate. And my ROC, if it is R here, what will be my ROC here? Nothing but R conjugate. But since we are considering only mod, right? Mod A or mod B, your ROC will still remain R itself. So only concerned with magnitude of the circle, correct? So you can write your ROC still as R. So again, if you take the case if X of n is real, then you have your X of n equal to X conjugate of n. And if you take Z transform on both sides, you will end up having X of Z equal to X conjugate of Z conjugate. So let's say X of Z as a 0 at Z0. Then what it means, if you substitute Z0 here, you will have Z0 star and this is equal to 0. So again taking conjugate, so if I have this, I take conjugate on this, I'll have X of Z0 conjugate equal to 0 conjugate, which is again 0. So this means that Z0 conjugate is also a 0. So they come in complex conjugate pairs. Similarly, for poles as well. So your zeros and poles come in complex conjugate pairs for real X of n. Of course, it is possible that there is only one 0, given that your Z0 is equal to Z0 star, which means that your pole or 0 location is real without any complex part or imaginary part, right? Okay, that is understood anyway. So next property will be convolution property. So here again, if my x1 of n has a Z transform x1 of Z containing ROC equal to R1 and x2 of n has a Z transform x2 of Z containing ROC equal to R2, then my x1 of n convolved with x2 of n is gonna have a Z transform x1 of Z into x2 of Z, and your ROC will be at least R1 intersection R2, because again there can be some pole 0 cancellation, and this convolution property is straightforward. So the derivation is similar to what we did in the discrete time Fourier transform case. So I'm not deriving it again here, I'm just stating it. Okay. So your next property will be differentiation in the Z domain. So what it means, if X of n has a Z transform X of Z with the ROC equal to R, then what will have a Z transform with dx of Z by dz. So it is again straightforward. I can derive it from this Z transform equation. X of n Z power minus n. So if I take a derivative, so it will come out to be X of n derivative of this. But what is the derivative of it? It is minus n into Z power minus n minus 1. So again, if I want to represent it in the Z transform equation itself, I need to remove this Z power minus n. So I'll multiply both sides by Z, and also this minus n I can take it to the left hand side. So minus Z dx of Z by dz is gonna give me summation n equal to minus infinity to infinity n x of n Z power minus n. So my n x of n is gonna give me minus Z dx of Z by dz, and my ROC is not going to change. Why? If you consider in the Z domain, taking differentiation will not remove a pole, correct? If you have 1 minus 1 minus AZ inverse, if you take d by dz of this, you'll only get twice the amount of pole into something, right? The differentiation will never remove this pole. So your ROC is going to remain same. Okay. So your next property will be first difference. So this is similar to differentiation in the time domain. So your x of n minus x of n minus 1. So this is also straightforward. It has a z transform of, so x of n has a z transform of x of z, and x of n minus 1 has a z transform of z inverse x of z. So this together is going to give me 1 minus z inverse x of z. So notice that if you take this as the product of two individual z transform, then if you notice this, so your mod z cannot be equal to 0 because this tends to infinity. So your ROC will be mod z greater than 0, and this ROC, let's say it is R. So together when it comes multiplication, your ROC will be at least R intersection mod z greater than 0. So it can also be that your z equal to 0 also is included because there is some pole 0 cancellation. But in general case, we write it as at least R intersection mod z greater than 0. So this is your first difference property. So next let us see accumulation. So in accumulation, what you have, you have summation k equal to minus infinity to n x of k. So how will it transform? So it is just the reverse of your first difference. So you can write it as 1 by 1 minus z inverse x of z. So this how will you write is, if you have y of n equal to summation k equal to minus infinity to infinity x of k, n here. So your y of n minus y of n minus 1 is gonna give you x of n, correct? And now if you take z transform on both sides, you can see your y of z into 1 minus z inverse is equal to x of z, and hence your y of z is nothing but 1 by 1 minus z inverse x of z. So this is your proof. And what is your ROC gonna be? So if you notice, the summation is a causal signal kind of thing, right? So this is gonna have ROC of mod z greater than 1 because there is a pole at z equal to 1. And similarly, if this has ROC equal to R, then what will be the ROC of them together? At least R intersection mod z greater than 1. So your ROC is at least R intersection mod z greater than 1. Okay. So next we'll see about initial value and final value theorem. So initial and final value theorem. So this again, the requirement is my x of n should be a causal signal. So which means that my x of n is equal to 0 for n less than 0. So in that case, I can write my x of z as summation n equal to 0 to infinity x of n z power minus n. So if we want to find x of 0, how do I find it? So again, if I write it out this way, there will be x of 0 plus x of 1 by z plus x of 2 by z in z square and so on until infinity. So somehow I want to remove all these terms. So what I'll do, I will take my limit z to infinity. So this will give me only my x of 0 term. All these will go to 0, correct? So my x of 0 is nothing but limit z tends to infinity x of z. Of course, what other thing I want? I want first my x of z to exist, which implies that each one of my x of 1, x of 2 are going to be finite. So that is a requirement always. So this is your initial value theorem. So you also have your final value theorem. Final value theorem. But you have one other requirement for this. So your ROC should contain z equal to 1, because your formula itself is limit n tends to infinity x of n is nothing but limit z tends to 1 z minus 1 into x of z. So this is your final value theorem formula. For this to be valid, your ROC should contain z equal to 1. So that is an additional thing for your final value theorem, and we'll also derive this. So we know that your x of n minus x of n minus 1 as a z transform 1 minus z inverse x of z. So which also means that your 1 minus z inverse x of z is nothing but summation n equal to minus infinity to infinity x of n minus x of n minus 1 into z power minus n. So another thing to notice here is your x of n is causal. So where will this n start from? So your n will start from 0. So n equal to 0 to infinity x of n minus x of n minus 1 z power minus n. So now we want to cancel all the terms except my x equal to infinity. N equal to infinity, which is x of infinity. So I have to find limit n tends to infinity here. But if I also tend my z to 1, then it will be like I'll have z of n. So z of infinity, or if I take any n, I'll have x of n minus 1 plus x of n minus 1 minus x of n minus 2 and so on, plus x of 0 minus x of 0. Correct? Or the other way around. I'll have plus x of 0, here minus x of 0 and so on. So all these terms will cancel and I'll be left with only x of n. And I can tend n to infinity. So what I'll do? I'll take limit n tends to infinity, summation n equal to 0 to n, x of n minus x of n minus 1, z power minus n. On the left hand side, I have 1 minus z inverse x of z. And now I take limit z to 1, 1 minus z inverse x of z. So this is gonna give me limit n tends to infinity. This limit z tends to 1, I can take it inside. So summation n equal to 0 to n, x of n minus 1, z power minus n. So this is gonna give me limit n tends to infinity, summation n equal to 0 to n, x of n minus 1. So this already as stated, it's gonna give me x of n only. So my limit n tends to infinity, x of n, which is nothing but my final value, is given by limit z tends to 1, 1 minus z inverse x of z. Or I can also write 1 minus z inverse as 1 minus 1 by z, which is equal to z minus 1 by z. And taking limit z to 1, z minus 1 by z is going to give me z minus 1. So I can also write this as limit z tends to 1, z minus 1, x of z. So that is what we have here. So you can write it in both the forms. This or limit z tends to 1, 1 minus z inverse x of z. So this requirement, what it also says. So let me put it here. So this along with x of n being causal. So your ROC is going to extend outward, right? Because the x of n is causal, and your ROC should also contain z equal to 1. So which means that all poles must lie inside our unit circle. So this is a requirement. Then only we'll be able to evaluate our x of z at z equal to 1. And this one z tends to 1 is for z minus 1 into x of z. So x of z into z minus 1. So this ROC only we are concerned about, because that only we are tending z to 1. Okay. So you need to be careful which ROC you are seeing. X of z may not fall in this, but your z minus 1 into x of z must be able to evaluate at z equal to 1. So we want this requirement. Okay. So next let us look at our common z transform pairs. So let us say we have a signal here, and then it's the z transform and its ROC. So our first signal will be delta of n. So this one, it's straightforward. Our z transform is 1, and our ROC is all the z plane, all points in the z plane. So second one will be a unit step sequence. So this is gonna have z transform of 1 by 1 minus z inverse. So this is similar to your a power n u of n with value of a equal to 1, right? And your mod z is gonna be greater than a. A here is 1. So third is similar to this, we have u of minus n minus 1 with a minus n. This is gonna give me the same z transform, but its ROC is gonna contain mod z less than 1. And if you have a shift in your unit impulse, so what will you have? You will have z power minus m, and again you will have all of z except 0 if my m is greater than 0 and infinity if my m is less than 0, correct? So this difference I'll have. So my next signal will be a power n u of n itself. So this we already know, we have derived it many times. 1 minus a z inverse, and my mod z is greater than mod a. Okay. And the sixth one, minus a power n u of minus n minus 1. So this is gonna have same z transform, but my ROC is gonna be less than mod a. So next, seventh one, if I add n a power n u of n, what am I gonna get? Using the differentiation in the z domain, right? What will I be getting? So if my nx of n is gonna give me minus z dx of z by dz, right? We just saw it, correct? So this one. So using that, what will we get here? So we'll be getting differentiation of this, which is nothing but 1 minus 1 by 1 minus a z inverse whole square minus 1 into minus a z power minus 2 into minus 1. And this we have to multiply with minus z. So what will we get? So this we'll get it as equal to, we have 4 minus signs. The minus sign will go away. So we'll have a z inverse by 1 minus a z inverse whole square. So this will be our answer. So let me put it on a side note here. And my ROC is gonna be unchanged, correct? So it will be mod z greater than mod a. So similarly for this case also, if I have minus n a power n u of minus n minus 1, I'm gonna get the same thing because the expression is same in the z transform. And mod z is gonna be less than mod a. So next, if you have cos omega naught n u of n. So cos omega naught n, you can write it as e power j omega naught n by 2 u of n plus e power minus j omega naught n by 2 u of n. So what transform is this gonna have? We'll have 1 by 1 minus e power j omega naught n by 2 z inverse plus 1 by 1 minus e power, this 1 by 2 I'll actually be coming as the term, and this n will not be here. So minus j omega naught z inverse. So if you try to simplify, what will you get? You will have 1 by 2 term here into, you will have 1 minus e power minus j omega naught z inverse plus 1 minus e power j omega naught z inverse by multiplication of this. So you will have 1 minus e power j omega naught plus e power minus j omega naught into z inverse plus this e power j omega naught will go away, z inverse square. So this, if you try to simplify, you will have 1 by 2 into 2 minus 2 z inverse cos omega naught, right? I can take z inverse common out and write this as 2 cos omega naught divided by 1 minus 2 z inverse cos omega naught minus z inverse square. So this 2 and 1 by 2 will cancel. I'll have 1 minus z inverse cos omega naught by 1 minus 2 z inverse cos omega naught minus z inverse square. And my ROC will be intersection of these both ROCs. So if you consider your mod A is equal to 1, so your ROC is mod Z greater than 1. So similarly for sine omega naught n u of n, you can write this as e power j omega naught n by 2j u of n minus e power minus j omega naught n by 2j u of n. So this is gonna have a z transform 1 over 2j by 1 minus e power j omega naught z inverse minus 1 over 2j divided by 1 minus e power minus j omega naught z inverse. So if you try to simplify, you'll have 1 by 2j into 1 minus e power minus j omega naught z inverse minus 1 plus e power j omega naught z inverse by 1 minus z inverse into e power j omega naught plus e power minus j omega naught minus z inverse square. So numerator 1 will cancel. So e power j omega naught minus e power minus j omega naught by 2j will get as sine omega naught and z inverse term is there. So z inverse divided by denominator is similar to this. So we'll get 1 minus 2 z inverse cos omega naught minus z inverse square. And your ROC is mod z greater than 1. So similarly, if you have r power n cos omega naught n u of n, you just need to append this, wherever this e power j omega naught term comes, you have to also add r there. So for cos, you will have 1 minus z inverse r cos omega naught divided by 1 minus 2 z inverse r cos omega naught minus z inverse square. And again, here your mod z is greater than r. Similarly for 12th one, if you have r power n sin omega naught n u of n, you will have r sin omega naught z inverse by 1 minus 2 z inverse r cos omega naught minus z inverse square, and your ROC is mod z greater than r. So these are the basic Z transform pairs we would require. And you can easily get back your inverse Z transform if you know this relation, and if you have your Z transform in this form, you can easily get back. Okay. So next let us discuss about analysis and characterization of LTI systems using Z transform. So if you have an LTI system with input x of n and output y of n and your impulse response h of n, you know your y of n is equal to x of n convolved with h of n. And in the Z transform domain, you know your convolution is gonna become multiplication. So we'll have x of z into h of z. And your h of z is referred to as your system transfer function. Or generally just the transfer function. And we again know the relationship for h of z. This is gonna be summation n equal to minus infinity to infinity h of n z power minus l. So now let us look at two important properties of our LTI system. So the first one is causality. So causality, what it says, your h of n should be equal to 0 for n less than 0, which means that your h of z is gonna be summation n equal to 0 to infinity h of n z power minus n. So if you observe, your h of n is a right-sided signal or right-sided sequence, and hence your ROC of h of z is going to be the region outside of the outermost pole. And again, since there are no z power minus n for n less than 0, so no positive power or no positive powers of z occurs. So z equal to infinity is also included in our ROC. Or we can also tell the other way. A discrete time LTI system is said to be causal if and only if the ROC of its transfer function is the region outside of its outermost pole, including z equal to infinity. So if this is true, then we can say our LTI system is causal. So this is the condition for causality which we derived from the Z transform. So just by looking at the region of convergence for h of z, we can determine the causality conditions for our system transfer function. So this also means that if my h of z being a rational function then my limit z tends to infinity, h of z should be finite, correct? So which means that the order of the numerator should at least be equal to that of the denominator, right? So it cannot be greater than my denominator. So this also follows from whatever we defined up. So next condition is stability. So let us look at the stability property of our LTI system. So for stability property, we know that our summation n equal to minus infinity to infinity mod h of n should be less than infinity. So this is equivalent to our mod x of z evaluated at 1 being less than infinity, correct? So x of z at z equal to 1 is nothing but summation n equal to minus infinity to infinity h of n. So mod of this is gonna be equal to mod of this, which is less than mod of this, correct? Because of the absolute summation property. So this is also gonna be less than infinity. So which means that my Z transform should exist at Z equal to 1, which means that my ROC should include Z equal to 1, the unit circle. So this is where the importance of the unit circle comes. Or in other words, you can also say that if my ROC includes, or I can say the other way, right? My discrete time LTI system is stable if and only if the ROC of its transfer function h of z includes the unit circle, which is given by mod z equal to 1. So I can say and discrete time, and here also it is mod z equal to 1. So now for a discrete time also LTI system to be both causal and stable, so we need to imply both the condition. Your ROC is going to extend to infinity, right, from the outermost pole, and it should also include the unit circle. So all the poles of h of z should lie within the unit circle, not even on the unit circle, because your unit circle needs to be included within the unit circle mod z equal to 1. So if this is your z plane, real and imaginary, and if you plot your poles and zeros of your h of z, so this is 1. All your poles should be lying inside, and zeros can be anywhere. It's not a problem. And your outermost pole, let's say this is your outermost pole, your ROC should include the unit circle. So it should be something like this. So next let us discuss about unilateral Laplace transform. Or Z transform, right? So in unilateral Z transform, it is similar to your unilateral Laplace transform, and it is for causal signals on systems. So it is defined as follows. So you have your, I'll write x like this to represent it differently from your bilateral Z transform. So it is going to be summation n equal to 0 to infinity x of n z power minus n. So my x of n as a unilateral Z transform x of z. I'm just representing it as a bigger size, different from the small x. Okay, it is represented this way, and most of its properties are similar. Most of its properties are similar to Z transform, which is also the bilateral Z transform, except for few. So we'll just discuss those few. So the first one is time delay. So if your x of n as a unilateral Z transform, x of z, and what will be your x of n minus 1. So it is 1 unit delay, unilateral Z transform. So this I have to find out. So this one, your x of z, you can write it as summation n equal to 0 to infinity x of n z power minus n. Similarly, your z prime of z equal to summation n equal to 0 to infinity x of n minus 1 z power minus n. So if you substitute as n equal to 0, what will you get? You will get z of x of minus 1 summation n equal to 1 to infinity x of n minus 1 z power minus n. So you replace n minus 1 with n. So then this will transform to x of minus 1 plus summation n equal to 0 to infinity x of n z power minus n plus 1, correct? Because this, you can write it as minus 1 plus 1. And this n minus 1 you are replacing with n. So you'll get this. And z power minus 1 you can take it outside. So x of minus 1 plus z inverse summation n equal to 0 to infinity x of n z power minus 1. So this is nothing but your x of z. So this is plus z inverse x of z. So this is gonna be equal to z inverse x of z minus x of minus 1. Sorry, plus, correct? Plus x of minus 1. So this is for time delay. So similarly, if you have n naught here, you will have x of minus 1, x of minus 2 into some z, z power minus 1 plus x of minus 3 into z power minus 2 and so on up to that n naught. And then here you will have z power minus n naught, something multiplying by that. So that one you can derive, it is straightforward. So similarly, your time advance. So if you have x of n plus 1, what will be your unilateral z transform? So we'll again see that your x of, I'll call it x double prime of z, is equal to summation n equal to 0 to infinity x of n plus 1 z power minus n. So this, you have to add another term to make it appear like your this term, correct? So firstly, I will take one z outside so that I'll get n equal to 0 to infinity x of n plus 1 z power minus of n plus 1. So then what I'll do, I'll add summation n equal to minus 1 to infinity x of n plus 1 z power minus of n plus 1 plus or minus, since I added here the x of 0 term I have added here, correct? Which wasn't there. This one starts from x of 1. So here n equal to minus 1 meaning I am starting from x of 0. So I also need to subtract it by 0. And z power minus n plus 1 for n equal to minus 1 will be 0. Z power 0 will be 1. So there will not be any coefficient here. So now this is nothing but if you replace n plus 1 with n, I'll have z into summation n equal to 0 to infinity x of n z power minus n minus x of 0. So this is nothing but z into x of z minus z x of 0. So that will be your unilateral z transform. So z into x of z minus z into x of 0. So these are the two differences. So you can see here there is a z inverse term, here there is a z term. This is expected anyway, but these extra terms also appear. So that we have to keep in mind. So similarly, we can extend this to any n naught. Okay. And because my x of n minus 1 is having this form, if I take my first difference property, which is denoted by x of n minus x of n minus 1, my unilateral z transform will be x of n, it is x of z, and x of n minus 1 what it is? It is z inverse x of z plus x of minus 1. So minus z inverse x of z minus x of minus 1. So this is gonna be equal to 1 minus z inverse x of z minus x of minus 1. So apart from this, all other properties are gonna be the same for me. So only wherever you do the time shifting, you have to be careful. And even in the accumulation case, since the signals are gonna be causal, so you will have your y of n equal to summation k equal to 0 to n x of k. So it is starting from k equal to 0. So again here you can argue that this is having x of minus 1, but this is just a general case. Sometimes your system may be causal, your signal may not be causal. So x of minus 1 may have some finite value. But here this is like your system, correct? So it needs to be causal, which means your k is gonna start from 0 instead of infinity. So that is all for today, guys. So in the next video, we'll be solving some questions based on your Z transform. So until then, take care. Bye-bye. See you.